Hello, my name is Rocio, and welcome to my Physics 2212 Lab 4 Circuits. In this lab, I'll walk you through different models, calculations, RC data, and some further understanding questions. In today's lab, we'll predict the behavior of a circuit containing resistors in series and parallel, use multimeters to measure the actual values of the conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. The fundamentals for this lab will be node rule, Ohm's law, loop rule, and the energy conservation equation. And note that there's no surroundings because this is all going to be computational. In Model A using PHYS, I created a circuit containing two 1.5 volt batteries, two resistors, one with 47 ohms and one with 100 ohms, and two ammeters. And I predicted that the currents I1 and I2 would be equal to 0.02 amperes because of the node rule, and I was correct. Here are my calculations. Then in Model B, I found that if we made one of the ammeters backwards, we would still get the same result in amperes. Then in Model C, when we replaced one of the ammeters for a voltmeter, I predicted that it would read 3 volts because there's the two batteries on the left and nothing on the right, and that was correct. And the ammeter now reads 0 because the voltmeter doesn't close the circuit. Then we proved the loop rule correct because after graphing the potential differences across the circuit, we found that the sums were they summed up to 0 volts, meaning that the circuit is conserved, and when we attach the voltmeter, we alter the circuit. However, the ammeter reading doesn't change because it has infinite resistance. Then in Model D, when we replace the voltmeter with an ammeter in parallel that has the 100 ohms resistor, the ammeter's reading is higher because we are now given a path for the current to avoid the resistor, and this is also proved by the Ohm's law. Using Ohm's law once again, we found that there were 48 ohms in the 47 ohms resistor and 102 ohms in the 100 resistor, and 0 ohms in both the wire and ammeter, so that means that there's no resistance in them. Then we got to build an RC circuit using a 9-volt battery, a 200 mF capacitor, and we switched between a 10 ohm and 20 ohm light bulb. And I found that the 20 ohm light bulbs dimmed a lot slower than the 10 ohms ones. And in the second part, we removed a battery, and I found that just in general, the light bulbs dimmed a lot faster. For our RC data, we took the natural log of the change in voltage over the initial voltage, which was 9 volts, and graphed it to be an almost perfectly straight line with the slope of negative 0.1685x that represented the inverse of RC. So RC, our time constant, has a value of 5.93 in this graph, but with the knowledge that we had, we found it to be 6 seconds, and so that means we had a 1.1% difference, percent error, which is really good. There were some errors in this lab, and some of them came from assuming that the current voltage wouldn't experience any effect from the voltmeter, and that's wrong because our readings were a bit off. To overcome this, we could use potential difference calculations instead. Also, our timing could very much have been inaccurate due to human nature, and our experiment was not done within a closed system, meaning that external forces would resort to incorrect values. Now I'll wrap up the lab with some further understanding. So what if in real life we did this and used an actual ammeter instead of an ideal simulated ammeter? Well, our current readings would be lower than what we figured since ammeters do have some resistance in real life. And next question is, what if we used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Well, in real life, our ideal model would backfire because there's no amount of resistance, so it'd be instantaneous and explode. And if we are completing the lab with real circuit components, use an ammeter to measure how long it takes to charge the capacitor when we connect it directly to the battery. Why is the measured time difference from the predicted time? Our model would not reach full charge as quickly as this and this would be because there's some amount of resistance that would slow it down. I hope you enjoyed this lab. Thank you.